This is a pretty big occasion. This is the first time I'm actually stepping back to do an exam from a class that I didn't take at Purdue. I took Calc 1 about a year ago, and I remember enough to do this exam. Let's say that much. But I just finished um, differential equations, and I'm about to start partial differential equations. So it's been a little while, but I remember some limits, and we're gonna give this one a go. Question 1, consider this function here over this domain. We're choosing the correct statement about its inverse function. So I'm going to go down here and rewrite this. We have y is equal to e to the, I'll simplify this down a little bit by moving this 2, multiplying that 2 by the exponent we have there, which is perfectly legal. E to the 2 absolute magnitude of x minus 5 plus 3. Now, since we're dealing with the domain from 0 to 1, so that's x, our x values are running between 0 and 1, what will this absolute magnitude always evaluate to? It should always evaluate to a positive number, but we will always have a negative number in here. So it's a little counterintuitive, but what we can do is that right there. We can turn it into a parentheses, and as long as we put a negative sign outside of it, because what this absolute value is really doing over this domain is always flipping the sign of what we have in absolute values right there from negative to positive. So this will do the same. So in order to solve for our inverse function, all we have to do is replace or swap the places of x and y. So x is equal to e to the negative 2y plus 10 plus 3. And we can simplify this a little bit more. We're solving for y. We can say that x minus 3 is equal to e to the minus 2y plus 10. Now we can take the natural log of both sides. We get ln x minus 3 is equal to the natural log of e to the minus 2y plus 10. The natural log of e to the something is just that something there. And what should we do now? Well, actually, let's factor out a negative 2 here. So we have y minus 5 and negative 2. Let's divide by negative 2 and add 5 to both sides. That gives us y equals negative ln x minus 3 over 2 plus 5. And that is our correct inverse, but what about finding its domain? Even though we know that our answer is B, since that's the only one with this inverse. What is its domain? Well, the domain of our inverse function is equal to the range of this function right here. And the range of that function is just going to be the set, just like this domain, that we get by plugging in these extreme values, so 0 and 1, to this guy. So if we plug in 0, we get e to the e to the 10 e to the 10th power, yep, plus 3. And if we plug in 1, we get e to the 8th plus 3. So I have these in reverse order, but you'll see that, that, oh, sorry, wrong one, although it's equal, that is the domain that we are getting right there. So B is our correct answer for number 1, and the answer key agrees. Question 2, choose the correct answers for the following questions A and B. Find all of the angles that satisfy this equation right here. Well, we can just directly solve this. We'll rearrange this to be 3 over 4 is equal to sine squared of theta. Taking the square root of both sides, sine theta is equal to plus or minus the square root of 3 over 2, because really this is just the square root of 3 over 4, but the square root of 4 is 2, so we get that right there. And where is this the case? Well, if I draw out a really crude unit circle here, sine of theta is equal to plus or minus root 3 over 2. here at pi over 3, here at 2 pi over 3, and then I won't draw out those angles, but here at 4 pi over 3, and here at 5 pi over 3. So you see that we've got the same plus or minus y, the same y level there for all those. I hope that sentence made absolutely no sense, but I hope you see what I'm doing there. So we're getting this set that A, C, and E agree with. Now let's solve this one. We are trying to find the sine of 8 pi over 3. Well, if I clean up this unit circle a little bit, what is 8 pi over 3? Well, we can go all the way around our circle once, and that's 6 pi over 3. And then we're right back where we started, and we're going another 2 pi over 3. So that takes us to 2 pi over 3 after going around all the way once. And what is this y level? This y level is root 3 over 2. Now we are finding the inverse sine of root 3 over 2, which is really just asking the question, how far do you have to go from the up from the x-axis in terms of your angle theta until you hit a y level of root 3 over 2, and that will occur first at pi over 3. So here we're just solving the inverse sine of what did we say that was? Root 3 over 2. So there we go. We get pi over 3, and our answer is C, and the answer key agrees with us there. Question 3, let's compute the following limits. So whenever you see some square roots running around in both of these questions, actually, we are going to multiply both the top and the bottom by the conjugate of this expression right here. And what that means is multiplying not by root 25 minus h minus 5, but we'll change that to a plus. So we're multiplying by root 25 minus h plus 5 on the top and root 25 minus h plus 5 on the bottom, just to keep things even. This will give us 25 minus h minus 25 on the top, just foiling everything out. And then on the bottom, we get h times root 25 minus h plus 5. So simplifying some things down, these 25s will cancel out, and we can divide an h out from the top and the bottom, and we get negative 1 over the square root of 25 minus h plus 5. Now, if we're finding the limit as h approaches 0, this becomes much easier, because when h is 0, we can just directly solve it. Minus 1 over the square root of 25 plus 5 is negative 1 over 10. So negative 1 over 10, negative 1 over 10. We are liking B and D so far. So for number 2, they actually give us a nice little kind of substitution that we can do that really helps us here. So they're telling us that x minus 1 is equal to all of this stuff. So let's apply that substitution. We have x to the 1/3 power minus 1 divided by, instead of x minus 1, all of this stuff. So x to the 1/3 minus 1 multiplied by x to the 2/3 plus x to the 1/3 plus 1. Now, this term and this term will cancel, and we're just left with 1 over x to the 2/3 plus x to the 1/3 plus 1. As x approaches 1, what will this thing approach? Well, yet again, we can directly evaluate that. When x is equal to 1, we get 1/3. So B is our correct answer for 3. Question 4, compute the following limits. Okay, so with number 1, we're going to do the same thing that we did earlier and multiply it by its conjugate on the top and the bottom, even though you can't really see the bottom, but we do have a denominator of 1 here. So to write this out, we're multiplying root x squared plus x minus x divided by 1 by the square root of x squared plus x over root x squared plus x. This gives us, this gives us x squared plus x minus x squared over the square root of x squared plus x. Now, our x squareds will cancel out on top. So now that we're at this point, we're going to do a little bit of a weird jump in logic, but you'll see how it helps us solve this in the end. We are going to divide everything by x. So we'll divide the top side, the top by x. So x over x will just give us 1. We'll divide this guy by x and this guy by x. We'll get a 1 here. And then what happens with this? Well, we can factor this x into this square root by squaring it. So we're really dividing by x squared in here. That gives us 1 plus 1 over x. And all of a sudden, we can directly evaluate this. As x approaches infinity, we only have one x to deal with. This little bit right here will approach 0. So as x approaches infinity, this expression will approach 1 over the square root of 1 plus 0 plus 1. And and that is just 1/2. So we have our answer already, but let's go evaluate this second one right here. So we're taking the limit as x approaches negative infinity of all of this jazz. And I'll write this out for us. X cubed plus 2 over negative 2x cubed plus the square root of 4x to the 6th plus 2. So there's actually a very cool shortcut that you can do that just allows you to solve this one completely directly. You really don't even have to write anything down. So what is the the highest power that we see on our in our numerator? We have x cubed, right? And then down here we have an x cubed. But how do we count the power of this guy under the square root? Well, really, this is another x cubed, because if we raise this whole thing to the 1/2 power, you multiply this 6 by that 1/2, and you get yet another 3. If we were just to take the square root of 4x to the 6th, we would get 2x cubed. So that is good to know. What that lets us do is completely disregard a couple things. This 2 is not going to have anything to do with our solution. It's just because we're approaching negative infinity, any constants, anything with a power smaller than 3 actually has no control over where we end up. So I'm going to get rid of that 2. I'm also going to get rid of that 2, and I'll take this square root here. We get 2. Well, actually, I think it'll be useful. It might be useful to keep this square root just for a second. So we have that square root there. What happens if we plug in negative infinity here? What is going to happen? In fact, what's going to happen if we plug in any value here? Let's just plug in negative infinity for the fun of it. So we have negative infinity cubed. We'll still call that negative infinity on the top there. It's a higher infinity, whatever. That gets a little crazy pretty quick. So then we have negative 2 times infinity cubed. We'll just call that negative 2 times negative infinity, or just 2 times infinity. And then we have plus the square root of 4 times negative infinity to the 6th power. That's just yet another infinity. And the square root of 4 infinity, we'll just call that 2 infinity. And what does this evaluate to? If we factor out an infinity, from everything and get rid of it, we get 1/4. And I hope you can kind of see how the ratio between the top side and the bottom side is, sorry, -1/4 is exactly that. It's -1/4. We have -1 of these guys on the top and 4 of them on the bottom. So it's this way of evaluating these gets a little bit sketchy sometimes and can sometimes lead you down the wrong road. But if you end up with some expression that has the same power in multiple different places, and you don't have a power that's overwhelming all of those guys, you can just do this kind of thing where you directly substitute in the value that you're looking for, even if it's technically kind of illegal when you're dealing with infinities. So 4 is E. Question 5, choose the correct answer for the number of vertical asymptotes and horizontal asymptotes of this function here. So let's solve for our vertical asymptotes first. That involves finding the values of x and really factoring the denominator such that we can figure out how many values of x make that denominator 0. Because if we have a denominator that approaches 0, that's going to lead our function to go off to infinity and do some weird behavior, which will give us that kind of vertical asymptote. So solving for that, solving for this denominator equal to 0, the square root of x squared plus x is equal to 0, we can square both sides and factor. This is x times x plus 1 is equal to 0. The thing is, even though we have two values here, we have x is equal to 0 and x is equal to -1, which solve this equation, only one of these is a vertical asymptote, because this factor, because it appears in the numerator also, that means that it's a whole. It's not a full vertical asymptote. The only ones that end up being vertical asymptotes are factors that appear in the factored form of the denominator but do not appear in the numerator. So vertical asymptotes, we found 1. Now for horizontal asymptotes, what we're going to be thinking about for this question is the limit of f of x as x approaches -infinity and the limit as x approaches infinity of f of x. Because what we'll see is that these actually end up being different values here. Okay, what is the limit? What is the limit of f of x as x approaches -infinity? Well, because we have an effective power or degree of 1 in our denominator, because the square root of x squared, gives us an effective power of 1, and then we have a power of 1 in our numerator. The value that we get for this limit is just going to be the ratio between these two when we plug in -infinity, kind of symbolically. So if we plug in -infinity, we end up with -infinity, and I should be clear here, what I'm doing is kind of saying when we're approaching infinity, this plus 1 and this x have absolutely no control over the destiny of our function. They do nothing. They do nothing for us because these have the highest powers, so they have full control over what happens to our function when we're dealing with infinities like this. So really I'm just getting rid of those, and we could further simplify the denominator to the absolute value of x. So let's do that. Let's plug in -infinity. We get -infinity over the absolute value of -infinity. This gives us -infinity over infinity, which is -1. But what about this limit here as x approaches infinity? That will just give us infinity over the absolute value of infinity, which is 1. So because we get two different values that our function is approaching, we could graph this, and if we zoom out a lot, we would see this kind of behavior, something like that kind of thing, where we're getting closer and closer to -1 as time goes to -infinity, and closer to 1 as we approach positive infinity. So that gives us our two horizontal asymptotes. Definitely a weird question. this one. And checking our answer key, yes, 5 is D. 6, compute the following limits. We're approaching x is equal to negative 7 over 2 pi from the left of tangent of x. Well, if you don't remember, the tangent of x function has this kind of behavior, and every multiple of, every step of pi that you take past pi over 2 and to the left of pi over 2, it has these vertical asymptotes. So at 3 pi over 2, it will also be doing this kind of thing. At 5 pi over 2, the same thing. And if we walk to the left a little bit, at negative 7 pi over 2, it will also have that kind of behavior. And no, I should be clear. It's not in the middle. This negative 7 pi over 2 should not be in the middle. It should be negative 7 pi over 2. There we go. It is that asymptote right there, just like pi over 2 is our first asymptote here. And these are increasingly sloppy over here, but hopefully you get the point that negative 7 pi over 2 is an asymptote. So what happens if we approach this from the negative side? That's coming from the left, and as we approach negative 7 pi over 2, what is our function doing? It is going off to infinity. So there is our answer for number 1. What about this second limit that they're having us take? What about this? We are approaching 1 from the left. But since we have this thing that looks like it pretty well could be factorable, let's see if we can do that. We can factor the numerator into x minus 3 times x minus 2 and factor our denominator as x minus 2, x minus 1. So then crossing our terms off like that, we are just left with x minus 3 over x minus 1. And as we approach 1 from the left, what is that going to mean? Well, we can use some number that's very close to 1 from the left to be able to figure this out. So let's plug in x is equal to 0.999 on the number line. You know, that's right before 1, and it comes on the left side of it. So that's a perfectly valid number for us to plug in here. And really all we care about is what signs we're dealing with. So on the top, 0.999 minus 3, that gives us negative something. And on the bottom, 0.999 minus 1 gives us minus something very small. So the denominator will be approaching 0, but from the negative side. We can cancel out both of these negative signs, and as this guy approaches 0, which is what will be happening as we approach 1 from the left, this whole expression will approach infinity. We'll end up with, you know, some negative number, let's say negative, like, I don't know, it doesn't actually matter what's in our numerator. And then on the bottom we have negative 0.000001, and we keep adding zeros as we get closer, and I hope you see how that will blow up to infinity. So E is our answer for number 6. Question 7, determine the values of the constants of a and b such that the function is continuous everywhere. So since this function is piecewise and kind of splits at the point x is equal to 1, we immediately have a big problem to deal with, which is that this function here seems to be undefined at x is equal to negative, at x is equal to negative 1. We will get a denominator of 0 here. So in order to fix that, we would really like a value of a such that we can factor our numerator and that one of our factors is x plus 1. So let's see what we can do. If a, just off the top of my head, if a is equal to 2, we can rewrite this as x plus 2 times x plus 1 and divide that by x plus 1. That's equal to x plus 2. Perfect. That simplifies things a lot. So now if if a is equal to 2, let's figure out what that implies for b. So at this point, I'll kind of draw what's happening. We have this function that's coming up to meet another function, and we have to adjust that second function up or down with that b value in order to kind of make them meet so that our functions are continuous. I can drag this guy up, and you'll see, we found the right b value. Look, our function is continuous. We can run our finger all the way along it without having to pick up our finger at any point. So let's plug in x is equal to -1 to this function right here to see what this guy will have to evaluate to in order for our functions to meet in the middle. So I'm getting 1 there when we plug in x is equal to -1 here. Let's set that equal to this thing with x is equal to -1 plugged in for x. We get -1 plus 3 plus b. Subtracting 3 from both sides, -2, adding 1, -1. That gives us b is equal to -1. So there we go. There's our solution. A is equal to 2 and b is equal to -1. So really it's just about making that little kind of sort of leap in logic at the beginning to recognize that you really need to get rid of this denominator here to pick 2 as your value for a. But once you get past that, you are sailing smooth. Question 8. Suppose we have a function f of x whose derivative at x equals 3 is equal to 5. That is to say, f prime at 3 is equal to 5. Evaluate this limit. This is a very scary question. And I'll let you know, we can solve this without dealing with any of this crap down here. I don't even remember what any of that means. I know it's something to do with the limit definition of a derivative at a specific point, but we don't have to care. We don't care about that at all, because what we can do is kind of hack the question. Let's find a function whose derivative at x equals 3 is 5. The simplest one for that is f of x is equal to 5x. It doesn't matter what x value we choose. This always has a slope of 5 at any given point. So now what we can do is plug in these two guys for our x in f of x, and then just evaluate our limit directly. So we have the limit as h approaches 0 of f of 3 plus 4h. So that's going to be 5 times, instead of x, we have 3 plus 4h, minus our function 5x evaluated at 3 minus 2h. So 5 times 3 minus 2h all over h. And this is great for us, because if we expand this, we will get 15 plus 20h minus 15 plus 10h over h, which simplifies even further to 30h over h. And we can just cancel those out, and the limit of 30 as h approaches 0, we got no h's left. It doesn't matter. That is just 30. So 8 is C. Yeah. So although it was very helpful, if we scroll back up here, when they gave us, this substitution to make, don't always listen to them. If you can do the problem in your own way, like this, go for it. That's a much cooler way of solving these in general. Question 9. Find the equation of the line tangent to this curve and parallel to that line. If there is more than one such line, list all of them. So, okay, we know that we want our line to be parallel to this thing. That means that the slope of our line has to be 7, because the slope of this line is 7. Okay, great. We also want to be tangent to this curve right here. And where are we going to be tangent to this curve? Well, if I kind of draw this out, And I'll simplify this. I won't use a cubic function, I'll use a quadratic function. But let's say that we were trying to find the spots where a line with a slope of 2, say, would be tangent to this curve. Well, that would only occur when the slope of the curve we're trying to be tangent to is also equal to the slope of our line. That's going back to our definition of the derivative as the slope of the tangent line at a specific point. So if we solve the derivative of this function right here and set it equal to 7, we will get all the values of x such that that works out nicely. So what is y prime? Well, applying the power rule, I'm pretty sure that's what it's called. It's been a long time. We don't talk about that kind of stuff anymore. What we're going to do is multiply this 3 down into this 1/3, and then decrement our exponent by 1. So we will end up with 3 times 1/3 x to the 3 minus 1, and then we'll do the same over here. Because we have an x to the first power, we will subtract 2 times 1 times x to the 0th power. Simplifying this out, y prime is equal to x squared minus 2. Great. Let's set this equal to 7, because we know that's what we want our y prime, our slope, to be. So 7 is equal to x squared minus 2. This has solutions for x is equal to plus or minus 3, which is great. So when x is equal to 3, what is the y value? What is the y value of this curve here? Because just like I was drawing out earlier, right now we have a line with a certain slope, and we know which points we want it to be tangent at. We just have to now shift it down a certain amount or up to be tangent at that point. So let's plug in x is equal to 3 to this equation right here. So for x is equal to 3, what do we get? We get 1/3 times 27, that's just 9, minus 6, so 3. And for x is equal to negative 3, we plug that in, we get negative 9 plus 6, which is negative 3. Now, what that means for us is that we can set up the point slope formula for our line at both of these points. Our point slope formula goes y minus y0 is equal to m times this is our slope, m times x minus x0, where x0 and y0 are these points that we have solved for here. This is our I'll actually make these into sets. We just solved for x0 and y0 here, so we can say that we know that we need to pass through the points 3, 3, and negative 3, 3. There we go. Okay, and our m is 7. So let's make these two lines because we have 2 points to deal with here. We have y minus y0. Let's use this first point. So y minus 3 is equal to m, which we know has to be 7, times x minus x0. And then for our second line, we will have y plus 3 is equal to 7 times x plus 3. These simplify out to y is equal to 7x minus 18, and y is equal to 7x plus 18. And that is it. That is answer choice C for number 9. Question 10, from the intermediate value theorem, which of the following intervals contains a root of this equation? Okay, all we need for this is a little table here. We'll have x and, I don't know, actually, I'll do one little step before we start solving anything. Let's grab this thing and say that this is f of x cubed minus 5x. So now what we can do is evaluate f of x at a bunch of different points, and if we find a point, if we find an interval on which, let's say that at the beginning of our interval, our value for f of x is 12, and at the end of our interval, our value for f of x is 20, and we're looking for our function to pass through 13. It must have passed through 13 at some point to get up to 20. There's no way. You can't go around the thing. It extends. You know what I mean. There's no way to get all the way up to 20 unless at some point within that interval you passed through 13. So we'll use that to our advantage. It looks like they are dealing with intervals from -1 to 4. So -1, 0, 1, 2, 3, 4. Let's evaluate all of these. Plugging in -1, we get 4, 0, 4, -3, 27 minus 15 is 12. Ooh, look at that. And then what if we plug in 4? We will get 64 minus 20, so 44. Look at that. In between these two, in between this interval, there must be some value of x for which this thing is equal to 13. So that will be a root of that equation right there. And so between 3 and 4 is our answer. That's E for number 10. Let's find the exact values for the following A and B. So while you may be tempted to just pick E because, 2/3, -2/3, those aren't values that we've had to memorize off of the unit circle, we can still deal with this. We're finding the inverse cosine of 2/3. That's the angle at which cosine, so our x value, is equal to 2/3. I'll eyeball that. That's about there. I'll call that theta. Then the inverse cosine of -2/3, well, that will just be over here. And I'll measure its angle all the way up there. That is that's theta 2. That was theta 1. So these are our two angles right here. Essentially, with these with these inverse trig functions, the question that we're answering for ourselves is what angle is cosine equal to this? What angle is cosine equal to this? And now the nice thing is, and you can just eyeball this out or think about it in a little bit more of a rigorous way, but what happens if we add these two angles together? Well, we are going to get exactly 1 pi. And that works out really nicely. So there we go. We are agreeing with A and C so far. Let's grab another, actually, let's grab a copy of this and get ready for our second one. We're looking for the sine, the inverse sine of 2/3. Yeah, that'll occur about here, where, no, that's a little too much. Where our y value is 2/3. That's still a little high, but you know what I mean. That's theta 1. And then the inverse sine of -2/3. That'll just be down here, theta 2. What happens if we add these two angles together? Well, we're just going to get 0. This one is just negative this one. So A is our answer for number 11. Question 12. Choose the right answers for number 1 and 2. That's kind of hilarious. I haven't seen another question in all Purdue Math where they tell you specifically to choose the right answers. Don't make sure not to choose the wrong answers. Okay, let's simplify this a little bit. We have the log of x squared plus 3 times the log of x is equal to the log of 32. What can we do? Well, one of our properties of log says that if we're multiplying a log by some value, we can just move that into the exponent of whatever is inside of our log. Then what we can do is raise each side, take e raised to each side, and this will simplify things out a lot. This will give us, and in fact, just to make sure we don't make any mistakes anymore, we can apply a second property of logs, which says that if you're adding two logs together, you can just make them into one log and multiply their contents as long as their coefficients are the same. So x squared times x cubed is what we'll have in here. That's just x to the fifth. Okay, that makes our simplification a little less sketchy because now e to the, sorry, I'm so used to dealing with natural logs. No, we're not raising e to both sides. We're raising 10 to both sides. Oh, I'm so sorry about that. So doing that will give us x to the fifth on that side and 32 on that other side. Because remember, whatever base we have, so these are log base 10s. If we raise 10 to the log, we will just get whatever is left over in here. And that's why I was doing an E, because in the higher Purdue maths, really all you deal with is natural logs and e's a lot of the time. And so e to the ln x is something that happens pretty often. Okay, anyway, solving this thing, we just get x is equal to 2. A little bit boring. Okay, number 2, find the value of cosine when sine is equal to negative 5 over 13. And theta is between pi and 3 pi over 2. So that's this quadrant over here on our unit circle, where cosine will always be negative. Let's keep that in mind. Okay, so we know that the sine of theta squared plus the cosine of theta squared is equal to 1. We can use this to our advantage because the sine of theta squared in this case is 25 over 169 plus cosine squared theta is equal to 1. We can write this as 169 over 169, and subtracting 25 from it, we get 144, which square roots nicely. We will get plus or minus 12 over 13. But what did we say right here? We said that cosine, our x value on our unit circle, will always be negative between pi and 3 pi over 2. So we can drop this positive bit, and we see the cosine is just equal to negative 12 over 13. That gives us C as our answer for 12. Okay, this is exciting. I'm done with my first MA 165 exam, which is weird because I feel almost more proud of myself for going back and learning this than I did for like differential equations or whatever. Anyway, I hope this was helpful for you, and see ya.